Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have Nina Balkin here. Nina was a postdoc with us, and since she's been at Georgia Tech, she's been a frequent visitor. She is a machine learning person, and she's going to talk about learning valuation functions.
Okay, thanks. So, as Jennifer said, I'll talk about learning valuation functions. On right now?
Yeah, it's better.
All right, so I'll talk about learning valuation functions, which is a topic at the intersection between machine learning, discrete optimization, and economics. And in particular, the motivation, or actually one of the main motivations of this work, comes from algorithmic game theory and economics. The model and the analysis are learning style, and some of the techniques that we use for proving our lower bounds and some of the structural results for our upper bounds come from discrete optimization. All right, and let me start with the motivation. So, as we know, one of the first steps in economic modeling is to model individuals as having valuation functions that describe how much value they place on different outcomes or events. So, for instance, their value for a vacation package in Switzerland, or their value for, say, a set of items in a shopping list for a supermarket. Right? And in this talk, we'll be focusing in particular on combinatorial settings, where we assume that we have a ground set of n items, say, for instance, the items for sale in a supermarket. And then the valuation functions will be over different bundles or different subsets of that item, of that set, of the ground set that the user might be considering. And more specifically, the question that we'll be looking at is, if we don't know the user valuations function, how can we learn it based on observed data? And I think this is an important question motivated by several applications. For example, it is very common for supermarket chains today to keep track of the purchases of our customers, for instance, by using loyalty cards, right? And so given access to all this data, it will be very useful for them to learn the valuation function of a customer or the valuation function of a typical customer in order to target, say, advertising, coupons better, and ultimately do better pricing, right? Similarly, companies like Expedia or Orbitz could hope to learn the valuation function of a customer based on past purchases in order to make better recommendations, right? And in the end, again, to obtain better profit. Right? And so motivated by such applications, in this work we study the question, the problem of learning interesting, rich classes of valuation functions based on observed data. And I will now briefly describe the classes of valuation functions we'll be looking at in this talk. And then in a few slides, I'll make the learning model that we consider in the talk precise. Right, again, recall we are in a combinatorial setting, so we have a ground set V of n items, for instance, a set of items for sale in a supermarket. And given a subset S of this ground set, we denote by f of s the valuation or the value that the user has for set S. And throughout this talk, we'll be looking at learning interesting classes of subadditive valuations, which express substitutes but no complementarities. And formally, a valuation function is called subadditive if for any two subsets ST of the ground set, we have that f of s union t is upper bounded by f of s plus f of t. And I will also assume throughout the talk that these valuation functions are non-negative and also monotone, so the customer never minds having more. All right? And more specifically, I'll be looking at learning two interesting subclasses of subadditive valuations, namely submodular valuations and XOS valuations. And these are both well-studied classes of valuation functions in economics, algorithmic game theory, with submodular valuations being a subset of XOS valuations, and XOS valuations being in turn contained in the class of subadditive valuations. And in fact, I'm going to spend most of my talk talking about learning submodular valuations and submodular functions more generally. And this is actually based on joint work with Nick Harvey, and it was in part done when we were both postdocs at Microsoft. And towards the end, I'm also going to talk about learning XOS valuations, and this is joint work with Florin Constantin, Satoru Ibata, and Lei Wang.
What does XOS stand for?
I'm going to define it. So it's, I'm going to, basically, it's a function that can be represented as a depth to 3 max of sums. I'm going to go to the definition later on. All right, so let me start by talking about learning submodular valuations. And actually, perhaps everyone here knows the definition, but still let me go quickly through it. So if we are given a ground set V of n items, then a set function defined over all subsets of the ground set is called submodular. If for any two subsets S and T of the ground set, we have that f of s union T plus f of s intersect T is upper bounded by f of s plus f of T. So clearly, if the function is non-negative, then any submodular function is also subadditive function. And actually, it's well known. One can show that a function is submodular if and only if it satisfies an intuitive notion of decreasing marginal returns, which says that for any two subsets T and S of the ground set, if for any such a T is a subset of S, for any x not in S, we have that the marginal value of x given T is greater than or equal to the marginal value of x given S. So for instance, the value to you, say, of a new box of cereal is lower if you already have cereal in your cart. Right? Now, let me mention a couple more mathematical examples of submodular functions. So first of all, it's well known that the rank function of a matroid is submodular. So for example, the rank function of a linear matroid is submodular. So here we are given, say, n vectors, say in Rn. And then the function f of s defined as the rank or the dimension of the space spanned by vector in S. So this function can be shown to be submodular. And one can easily show this by just noticing that if you add a vector v, if adding a vector v to a set S would increase the dimension of the space spanned, then it would also do so if you add it to a subset S prime of S. Right? Now, another classic example is if H is concave and the function f of s defined as h of size of s is submodular. All right, and as I mentioned a few times, in this work we look at learning such functions from data. And in particular, we consider a distributional learning setting and develop a PAC style analysis for this scenario. And informally, the learning model we consider is as follows. We assume that we have some source of examples, some source of unlabeled examples. These examples then get labeled according to some target function, say the valuation function of a customer. And these labeled examples are then input to a learning algorithm, which then produces a hypothesis function. Right? And then what we want is to guarantee that with high probability, the function that we output is close to the target function. Okay? More formally, in the training phase, the learning algorithm is given a set of polynomially many labeled examples. These examples are assumed to be drawn IID from some fixed but unknown distribution over subsets of the ground set. And we also assume that these examples are labeled according, again, to some fixed but unknown target function, which for now I'm assuming that is submodular, non-negative, and monotone. And then what we want, our goal is to out a hypothesis function G that with high probability, say with probability at least 1 minus delta, over the draw of the examples in the training set, provides a good approximation to the target function on most of the examples coming from our distribution. Right? And here by most I mean this 1 minus epsilon factor, and by a good approximation I mean a good multiplicative approximation. So, well, for this model, no, absolutely, yeah. So this is just the definition of the PMAC learning model for real valued functions, right? But just to make the discussion concrete, you can think about the target function as being submodular for now.
So now you have 3 parameters, epsilon, delta, and the alpha.
Right, so precisely. So we want to be high probability. We want to be mostly approximately correct, right? So we want, that's why we call this model the probably mostly approximately correct learning model, or the PMAC learning model. And when alpha is 1, we actually recover the classic PAC learning model for learning Boolean functions.
So the important change is not only that you introduce a new letter, but you change the
permit it a
roles
little
of the
bit.
letter.
Well, the original model.
Approximate was the epsilon, and now it's
Well,
alpha.
it should have really
So
been
what is the mostly now? The
for
mostly?
1 minus epsilon.
Ah.
So the original model should have really been called probably mostly correct, because this is what
Yes,
really
it
happens.
should. It should.
But probably the name wasn't so
Very
nice, so it chose PAC as opposed to PMC.
That's true.
But in our case, PMAC sounds very nice. So.
Is it obvious that this would be the natural way to measure correctness?
So that's a good question, actually. I like these questions. For instance, an alternative, something that, an alternative way to define success is to try to minimize the square loss, where here you would minimize the expected value over S of the f of s minus g of s squared, right? So this is the target function, and this is a hypothesis function, right? And right, so why aren't we doing that? Well, first of all, we chose to go with the PMAC model, the PMAC loss, because really that allows us to compare better our results with the previous results known in the optimization literature, in the discrete optimization literature. So that's one reason. It really aligns better with the optimization literature. Now, a second reason, actually, I think that the PMAC loss is interesting in itself because it allows us, the lower bounds in this model are more meaningful. So it really allows us to get a more fine-grained control of errors. So in particular, it allows us to distinguish between the two cases. The first one is where you have a low error on most of the distribution, but an incredibly high error just on some small fraction of the distribution. And the other one is where you have moderately high error everywhere. And so this PMAC model allows us to distinguish between these two cases where the square loss doesn't quite do that well. Yes, but our lower bound will also hold for the square loss.
Yeah, it looks like if you put in, instead of doing squared error, you do the expected log of f minus log of g.
Well, it depends how large is the range. I mean,
no, but I mean, then your results would imply something for that one. Because, well, then that would be another natural measure. And your results would be strong, would imply.
Sure.
Results there,
Right.
But I guess my concern is that if I take a valuation function and I add a constant to it, I don't change the ordering over the bundles, right? So if I think only the ordering information is relevant, and that the function I'm just simply using as a compact representation of the ordering,
Yeah.
then it's not so clear that I care about f being less than or equal to alpha times g.
Okay. Right, but you can also argue if you scale it, then it's not clear that you'd care about the other one.
Yeah.
So I guess for each, right? So for each loss, you're going to find a criticism.
Can you repeat for me just which one is the probable, which is the mostly, and which is the approximate for parameters?
Right, so the probably one is the simple one because it's obvious. So if high probability, right, over the draw of the examples in the training set, right? You want to be mostly, so on most of the points, you want to be approximately correct, like approximately in an optimization sense, right? You want to be a multiplicative factor of alpha of the target function on the state.
She added this green.
Right, we thought we really added.
She added green, but she changed the names.
Right.
To protect the innocent.
But for a good reason, because this is really the right naming.
But then again, the same thing you could say if somehow, this is sort of in the natural units where log
See, when less defined,
make
So
it
if
a
it's,
log
if
of
it's
the
your
Can't
income, the
call
only
the
thing you
approximate
care about is how many
the
digits.
1 minus epsilon.
Yeah,
He didn't have an
exactly.
optimization.
Actually, he did not define the, he did not come up with the name. Dana Englin came up with the name. In the original paper, we did not have a
Oh,
name.
yeah, he didn't. That's right. Theory of the learnable, he didn't say.
Have a name, yes.
Yeah,
So
that's true.
who's responsible for the wrong name?
Dana Englin.
Oh, really? Not?
Not Valiant. No, no,
Yeah,
no.
actually, he didn't in Theory of the Learnable, he didn't use the name. That's true.
Yes?
This is a very naive question. Are we learning D also, or is D given?
No, it's fixed but unknown, but you can sample. Like in a learning setting, you can sample examples that are drawn ID from D, and you get to see the value of the target function.
So D may be more complex that you may not be able to learn it, but you might still be able to learn F on D.
Sure.
So how does the supermarket do that?
Let's go back to this question at the end, the discussion phase. No, actually, but I don't want to go into it right now, but it's a good question for discussion at the end, because I will have answers for it. All right, so now given this model, so here are our main results within this model. So first of all, we can show a general upper bound. So we can show that there exists a polynomial time algorithm for PMAC learning the class of non-negative monotone submodular functions with approximation factor of square root of n. Here, remember, n is the size of the ground set, right? So given this, maybe this might not sound so impressive, right, at first, right, because n is the size of the ground set. But surprisingly, and this is the surprising part of this work, we show also a very strong lower bound. So we can show that any algorithm that only uses a polynomial number of examples cannot PMAC learn the class of non-negative monotone submodular functions with an approximation factor better than n to the 1/3. It's, yeah, information theoretic. Right.
A poly n sample size?
Yes.
Or
Yes.
For any poly?
Yes. And actually, this result also holds even if the underlying distribution over the unlabeled examples is known, and even if we augment the model to allow value queries. So even if we allow the algorithm to adaptively pick sets, subsets as a ground set, and to query the value of the target function on those sets. All right, this is in the worst case, however, over the distribution. In the case when the distribution is nice and we are trying to learn Lipschitz submodular functions, we can get a much better, essentially a constant factor approximation guarantee. And I'll talk about this. This follows from concentration results of submodular functions.
What is the product distribution? It's a product distribution over.
So this is just in the nice. So this, the general upper bound and general lower bound are in the worst case of the distribution. In the worst case. But the product distribution, right, in the case when you have a product distribution over the element, right, so over the elements of this, over the n elements, right, then we can get a much better result.
So you talk about this result also later?
Yeah. I'll talk about, actually in the next part of my talk, I would like to talk about some of the key ideas improving all of these results. And I'll start by talking about the general upper bound, which again is that we have a polynomial time algorithm for PMAC learning the class of submodular functions, non-negative monotone submodular functions, with an approximation factor of square root of n. And since actually it's simpler to think about it, I'll first describe a weaker upper bound for the an upper bound of n for the more general class of subadditive functions, and then I'll mention how to modify to get what we want for submodular functions. Right, and here is a simple structure result for subadditive functions. We can show that any non-negative monotone subadditive function can be approximated to within a factor of n by a linear function g. And yeah?
Just clarification. How do you sample from the distribution in general case?
It's an arbitrary distribution over subsets of the ground set.
So the distribution is arbitrary over the subsets?
Yes.
And
In the for the general result,
and
right?
in the product case, you have some null element or something like that, or
Again, in the
you
product.
have some null element because you're getting the product distributions over each of the n slices, right? And
Yeah, and what do you mean by null element? If you can have probability 0 of, yeah. What do you mean by null element? So you can have basically, you have.
The empty set.
yes, you can ask because all the in the product distribution case, do you have always had n elements in each set?
No, because what you do, you sample. So what I formally mean by that, you have probability P1 for getting item 1 in your set, P2 for getting item 2, and so on. Probability P1 with item 1, probability P2 with item 2, and so on, and form a set. So this is what I mean by product distribution. But for what I'm talking about right now, I'm assuming an arbitrary distribution over subsets of the ground set for the most general upper bound. All right, and as I said, here is a simple, I'm going to start with a factor of n upper bound for subadditive functions, and because it's simpler to describe. And this is based on a simple structure result, it's really trivial structure result that says that any non-negative monotone subadditive function can be approximated to even a factor of n by a linear function g. And all you have to do is to just verify that this function g of s, which is defined as sum over xness of f of x, satisfies the desired inequality, which is that g of s is upper bounded by n times f of s and lower bounded by f of s. And this part, the first one, the first inequality follows just from subadditivity because the function is subadditive, and this one follows from monotonicity. Right? So visually you have a picture like this. Right? And so now given this fact that, again, I stole it from Nick. I agree. Right, so given.
I'm going to make you draw pictures.
Right, so given this fact that any subadditive function can be approximated within a factor of n by a linear function g, if you think about it, this then implies that examples, labeled examples of the following form are linearly separable in Rn plus 1. And so examples are of the form chi of s, f of s plus, and chi of s n times f of s minus. And here chi of s is a feature, it's a indicator vector for the set S. And so this is a feature part of our examples. Chi of s, f of s is a feature part, plus is a label part, and chi of s n times f of s again is a feature part, and minus is the label part. And again, an immediate consequence of this structure result is that labeled examples of this form are linearly separable in Rn plus 1. And so this then immediately suggests trying to reduce our problem to the problem of learning a linear separator in Rn plus 1. Right? So what we could do is we could try to map our original examples into Rn plus 1 this way. Then we could try to learn a linear separator there, and then output a linear function induced by that linear separator. And then in order to prove correctness, we could try to use standard generalization bound or sample complexity techniques for Boolean functions, like VC dimension techniques, right? However, there is a slight problem. Examples of this form are not really independent, right, clearly. So these examples are not independent. And so we need a slight trick here. And in particular, starting from the original distribution, we create a new distribution in Rn plus 1 as follows. So in order to sample a point from this distribution, we first sample a point from the original distribution over subsets of the ground set. We then flip a coin. If it comes up heads, we add this positive example. Otherwise, we add this negative example. And then we can argue that a linear separator with a lower on this new distribution in Rn plus 1 induces a linear function that has a good approximation, has an approximation factor of n on most of the examples coming from the original data distribution over subsets of the ground set. Okay, so basically given this fact, now our algorithm is as follows. It gets as input a training set of examples, S1, f of S1, and so on, Sm of f of Sm. For each set Si, we flip a coin. If it comes up heads, we add this positive example to the training set. Otherwise, we add this negative example to the training set. And then we learn a linear separator in Rn plus 1, right? And then we output a linear function induced by it. And now we can use standard generalization bounds techniques to argue that if the number of examples we see in the training set is roughly n over epsilon, then with high probability, the function g that we output approximates the target function to within a factor of n on 1 minus epsilon fraction of the examples. Right? So this is for subadditive functions. Now in the case when the target function is a submodular function, we can use a stronger structural result due to Gaumans et al., which says that any non-negative monotone submodular function can be approximated everywhere to within a factor of square root of n by square root of a linear function. Yeah. And then so we can use this result and then slightly modify our algorithm, replace f with f squared, slightly modify the function that we output, and then a similar reasoning as the one that I had for learning subadditive functions will allow us to conclude that if the number of training examples we see is roughly n over epsilon, then the function g that we output approximates the target function within a square root of n factor on a 1 minus epsilon fraction of the distribution. Right? And let me also mention that this result is actually also robust to variations. So in particular, we can get a similar result even in the case when the target function is not necessarily a submodular function, but say is within a beta factor of a submodular function everywhere. So the same result would go through, and we just the beta factor just goes into the approximation ratio, right? And similarly, also we can also deal with the so-called agnostic setting, where the target function is not necessarily submodular, but agrees with a submodular function on all but a net fraction of the points. And again, the same result will go through from some.
When would that ever come up? Where you would have that it.
Well, even for a valuation function, might not be fully submodular, but it might be somehow close to a submodular function. Actually, I think that most often probably that's true when.
Oh, because it's just noise.
Yeah.
Perceptron to learn that the function, it's a linear.
Well, if perceptron, right? Well, but perceptron is not fully polynomial. Only if you have a large margin of polynomial, you can just use LP. Linear program.
You just solve the linear program.
Yes.
The linear program.
But this is in the noise-free case, right? When we have noise, then we get the sample complexity results. We can learn with a small number of samples, but the algorithm is not necessarily efficient, computationally efficient, just because we inherit the hardness result for agnostically learning half spaces, right?
So if the function is not monotone, can you say?
So, well, as long as, so the cool thing of about this algorithm is that as long as you can show a structural result, right? So this argument, as long as you have a structural result, you immediately get an algorithm, and the argument just carries through.
Are there any
Actually, Nick mentioned to me that him and Satoru proved something about non-monotone submodular functions. I have not seen the proof though, so, but
They may exist a positive structure.
there is a positive result there. So they claim a positive result. I have not seen the proof myself. All right, so basically, to summarize, this is the main result for learning submodular functions, a square root of n guarantee on the approximation factor. Now, this is in the worst case. Now, in the case where the underlying distribution is a product distribution over the elements of the ground set, and we are trying to learn a Lipschitz submodular function, then we can get a much better learnability result. And this is actually based on some interesting concentration results of submodular functions. Just any item cannot increase the value of the function, say, by more than one.
Oh, just addition of the item.
Yeah. So f of s union x minus f of s is upper bounded by, say, 1.
Every singleton is at most 1. No, that's.
So matroids function satisfies this. But the Lipschitz constant, it doesn't have to be 1. It can be L, but then the vet will go into the in the guarantees, like in the approximation guarantees.
This is sort of somehow I mean, it's not scalable, right? I multiply the function by 2, multiply everyone's.
That's strange.
Everything's cost by 2, then it's no longer so.
You change the Lipschitz
I mean,
constant, right?
you shouldn't have to change anything. The approximation guarantee was set up so that scaling should not change.
It's true.
So say it again.
So the alpha doesn't need to double if I double f and g, right?
What if you measure in pennies instead of dollars? Then suddenly.
Well, so our PMAC loss takes care of that, right? Our PMAC loss takes care of that because it's a multiplicative loss.
Right.
So the definition of our loss takes care of that.
So then what's important about, then I don't see why Lipschitz should be significant at all, because.
Well, if we have an addition, if additionally we have a Lipschitz function, then we can get better results.
There
We
must be
just
some
use
notion of.
But is the Lipschitz constant hiding in the big O?
Yeah, that's
Is the Lipschitz constant hiding in the big O? Where's the dependence on the Lipschitz constant, or does it matter?
I assume it's 1. So it all boils down, like if the function, you get different concentration results here, right? So
So what's the definition of Lipschitz here again?
So just f of s, so the f of s union x is no more than 1 plus f of s.
Okay, that's what Marcus had asked. Because you can always scale up and down, so can you just always get that?
Yeah, why don't you multiply
anything?
If you have Lipschitz constant 10 million, just divide, you measure in $10 million, and now you have everything.
So,
Maybe you'll see it in the next
Do you have a lower bound on your function?
Yeah, I mean, is there a thing saying that the smallest increment is also at least?
well, the learnability results depend on the smallest non-zero value.
Okay.
So maybe then the end will depend on the Lipschitz constant divided by the smallest number.
Yeah,
Right.
yeah, absolutely.
Okay.
Yes.
Then everything's
Yes.
fine. Yes.
So the smallest increment is also bounded, lower bound.
Yeah. Okay.
Right, so-
Good.
Right, and actually,
Now you can go.
just to make this simpler, let's assume for now that the function takes value, the smallest value is 1, just to make things simple.
You can't scale
Maybe
it
it
all
should be
the way.
Lipschitz this one?
No. Yeah.
Well, so just, okay, let me just for this slide and then I'll mention. So if it's not 1, if it's eta, then the approximation factor will be divided by eta. Right, but just because my slides here assume that it's 1, that's why I'm making this assumption. But again, if it's not, we can just easily fix it. All right, so now since we're looking at the regime of product distributions and Lipschitz functions, we can immediately use some classic tail bounds, like say the McDermott inequality, in order to argue that, in order to get a concentration result of the f of x around its expected value that looks like this, right? So it's an immediate consequence if the function says 1 Lipschitz, right? Now, and so this then immediately suggests trying to basically predict f of x by the expected value of the function, which is something that we can estimate from the samples, right? Now, unfortunately, this bound over here is only useful when t is like square root of n, right? Because otherwise this will become, t is at least square root of n, because otherwise it will become too large. And so if we want a constant multiplicative error rate, then the expected value of the function has to be at least square root of n, all right? And now, the cool thing, the interesting thing, is that if the function is submodular, then we can improve the tail bound. And in particular, we can show that this 1 over n factor here can be replaced by 1 over the expected value of the target function, or the expected value of the function. And this then allows us to get a constant multiplicative error rate on a constant fraction of the points, and and also a log 1 over epsilon approximation on a 1 minus epsilon fraction of the points.
I mean, the classic isn't, there's no n in the classic.
Well, no, you have n, so if the function is defined x1, x2, xn, there is n.
Yeah, but typically you talk about a Lipschitz in L2 norm, so you can get a stronger result. Right? You can say the function is Lipschitz with respect to x perturbed on an L2 ball. So you don't.
All right, so what I wrote here by classic, I really mean the McDermott bound, which is like Azuma. It's a very specific bound that I wrote down here. And it does depend on n.
But the Talagram ones are n.
Well, so this is like the question, how do you prove this? Well, the original proof was Talagram based. Our original proof was Talagram based. Even Jan von Trapp showed an even simpler proof based on self-bounding functions. Right, so if you use the right concentration bound, then you get this bound. The right concentration, the right tail inequality, then you get this bound.
Right.
So I guess Shyam's point is that n could have been other functions which depended on f and x.
Right, so this is exactly what we do. Right, so this is exactly what we do. So he mentioned Talagram. This is what we actually did. We applied Talagram to get this bound. But the most naive, the classic one, the super classic one, give you a factor of n here, 1 over n. And actually, this was not known before our work, so it has interesting consequences actually. So nobody, I mean, I don't think this has ever been written everywhere. But if the function is submodular.
You're saying the top bound, that's for the submodular case. Using the German, that's what you get.
This is for any Lipschitz function, this one. For any Lipschitz function, you get this. Now, if the function is submodular, then you also get this.
So what does the classic Talagram bound apply for this? Because there is a result for Lipschitz functions in Rn. And what does that imply here? Can you directly imply that for submodular?
Well, the Talagram talks about some self-certifying thing, and so I don't think that.
Classic bound for
I think that if you apply for an arbitrary Lipschitz function, you're going to get this. And actually, I think Jan Wondrak has a survey where he gives examples for subadditive functions that are Lipschitz, but you don't get such a strong result here. Right, and just to be precise, and by the way, so to go back to the smallest value of the function that is non-zero, right, so what we can show is that, right, so if you, right here I assume that the smallest value, basically how do I get from here to here? I just plug in t to be like, say, square root of log 1 over epsilon times the expected value of the function, and when t is greater than log 1 over epsilon, this just follows from this bound. When t is smaller than log 1 over epsilon, I just use the fact that the smallest value is 1, and then I get this approximation factor. Now, when the smallest value of the function is not 1, then the approximation is like eta, which can be, say, very close to 0, then this will go, the bound will be log 1 over epsilon over eta. Right, so there is.
So does submodular prevent the expectation to be 0?
No, and by the way, another thing that I assumed, okay, so I hided this. So even in the previous algorithm, so these are all, this way okay, I have to deal with the null space separately. So for simplicity in my talk, I assume that the function never takes the value 0. So remember, I assume that it's non-negative and monotone. And I also assume for simplicity that the function never takes the value of 0. But we can deal with that separately. We have to extract it separately. Because with a value of 0, if you just don't predict 0, then you have an infinity approximation ratio. So we can have to deal with that separately. But luckily, you can extract it separately. So this is just for the...
And getting near 0 doesn't create any problems for you.
As I mentioned, so if we allow, right, if the smallest value of the function is not 1, so like the smallest non-zero value of the function is not 1, then the factor here will be log 1 over epsilon, say it's eta, then the factor here will be log 1 over epsilon divided by eta.
Oh wait, then E of f of x is actually larger than 1. Oh, but it's not smaller than n. Okay.
Right,
I'm trying to just understand this
other result
I'm
is
confused
n.
by your box algorithm. So f is really just a function supported on a hypercube, right? Because you have p1 to pn, and f is a function x1 to xn supported on the hypercube. And you have a product distribution for each element. And this is 1x, just one sample is what you're giving the tail bound for, correct?
No, it's not one sample. So I should have, okay, think about this as being s, f of s. So it's, you have n samples. It's the empirical value of the expected value of the function, right? It's just f of s1 plus f of s2 all divided plus f of sn divided by m. It's basically it's an empirical estimation of the expected value of the function. So you get samples, right? So you have sets S1, S2, Sm that you see in the training set. You assume that each set Si is drawn from a product distribution. And then what this is just the empirical mean, exactly.
What is m here?
The number of samples.
And it doesn't appear in the bound.
N is the dimension.
N is the dimension. So usually the dimensions would appear in the bound, right? If you use the most naive inequality, I'm not talking about Talagram, because it's what we say, if you use Talagram, you get something better on the function.
Multiple samples. Talagram, the classic Lipschitz bounds are one sample on x1 to xn, and that's what the classic Lipschitz bound is for a function.
Right, but then you have to estimate, right? So this is, right. So sure, the bound itself doesn't include any empirical mean or something, but you have to estimate this from the sample. So in order to predict, right, you have to estimate them from the sample. If you have enough samples, you can easily estimate it. So right, the classic bound has no, right? It looks like this, or it looks like this.
So the bounds that are being stated are for single sample.
Right.
The algorithm is estimating E of f of x by sampling.
Okay.
Right,
Multiple
precisely.
samples, so
Which is separate from it. Yeah.
So since I'm even further, very far back, so the classical Chernoff kind of bounds that we tend to look at used to consider linear f. For general Lipschitz, there used to be something known, and you're saying for submodular.
You can do much better, yeah. Yeah.
Now, when f is submodular, E of f of x under the independent selection would just be the Lovash extension of the submodular function, right?
Okay.
Is that?
Lovash extension.
So if you're picking each object independently with probability pi, and f is submodular, then E of f of x would just be the Lovash extension of that function, right? Is that?
I'm not sure, is that right? Okay, so why is that relevant?
Well, so the low-Vash, sorry, so the low-Vash extension is convex, right? It's a, which way does it go? Convex?
So are you trying to see if this has implications also for convex function?
Yeah, I guess so. Okay, so I guess.
So right, the low-Vash extension is convex, but
right, okay, so the
I'm
low-Vash
not
extension is convex. So
for
this,
sure.
Okay.
And if this is the low-Vash extension, right, if A of f of x is the low-Vash extension, then maybe one has implication also for convex functions.
So here in the product distribution, you have no constraint on those the meaning of everywhere.
No.
So this probability bound does not
No.
for the closed uniform.
No. But as I guess everyone here observed, then the approximation factor does depend on the minimum value of the function. I said, as everyone observed, the approximation factor here does depend on the minimum value of the function.
I see. That somehow relates to this.
The scale.
Correct.
Yeah.
What is considered to be correct?
Yeah. All right, so let me also now talk about a little bit about the I think the most surprising result in this work. So I think this is good to know, but it was not. It's not necessarily the most. It's in the end an observation. Okay, now the most interesting result in this work is the lower bound. So we can show that that any algorithm that only uses a polynomial number of examples cannot PMAC learn the class of non-negative monotone submodular functions with an approximation factor better than n to the 1/3. And the high-level idea of the construction here is as follows. We're going to use the fact that any matroid rank function is submodular, and we're going to construct a new hard family of matroid rank functions with the following property. So the property is that there exist sets A1, A2, AL, which are subsets of the ground set, and there are super polynomially many of them. So for instance, think about L as being n to the log n. So there exist these super polynomially many subsets A1, A2, AL, the ground set, and there exist two values high and low, separated by roughly an n to the 1/3 multiplicative factors, such that for any assignment of low and high on these subsets, there exists a matroid in our family whose rank function achieves exactly that assignment on those subsets. Are subsets of the ground sets.
So these are.
Yeah. I'll just give more details about the construction in a minute. Right, but now once we have this picture, but there exists this set, super polynomially many of them, and there exists this two value high and low separated by a huge multiplicative factor, such that for any assignment of high and low of these subsets, you get that there is a matroid in our family whose rank function achieves that assignment. Once we have this picture, then we immediately get the n to the 1/3 lower bound for learning. Why? Because just imagine that the target function is picked at random by flipping a coin to decide between high and low on any of these subsets. And now clearly, no learning algorithm is going to be able to do better than just randomly guessing between high and low on any example it has not seen in the training set, right? And so, and if the underlying distribution is uniform over these sets, right, since the training set is a polynomial size, then in the training set we're only going to see a very tiny fraction of this set A1, A2, AL, so we're going to do badly on most of them. Because again, on anything we had not seen in the training set, the best we can do is just to just arbitrarily decide between high and low.
So the low value is the valuation of the sets, and the high value is the valuation. What fraction of people are in the highs?
So this is the point that exists. So to show that there exists 2 to the L, so basically 2 to the n to the log n matroid rank functions, such that for any single assignment of high and low on any of the subsets, no matter how you pick high and low in any of these subsets, there exists a matroid in our family whose rank function achieves that assignment. So this is what we show. And again, this then implies the learning lower bound, just because if you pick the target function at random by flipping a coin to decide between high and low, right, then no algorithm will be able to do better than randomly guessing between high and low on anything it had not seen in the training set.
So could you remind me what the matroid function is? Are you using like a coverage function?
No, it's just a matroid rank function that I'm going to remind you right now.
Okay.
Okay, but I wanted to first give the high-level picture of the argument.
So suppose if you can use like n to log n examples.
Sure, then you can.
But
Yeah, then you could.
you clearly beat this.
If you have value queries, for sure. If you can use a super polynomial number of examples, then especially value queries is trivial that you can learn it. You just query all those points.
Yeah, but in general, it's true too, that if you have n times log n, n to the power log n samples.
In random samples, I mean, I expect the error to decrease, but I mean, I expect to get a better bound, but I'm.
Is it still polynomial, or is it go to a much?
I did not compute it, to be honest, because usually in learning we only look at polynomial number of examples, but it's a good question. So, for sure it will be better, but the question is how better, I'm not sure.
Sorry, so this result also implies that if you want to learn a submodular function without any distribution, you can just ask any value. Then still it's going to work, right?
What do you mean, the lower bound?
Yes.
Sure, yeah. Yeah.
You mentioned it, you can query it.
Yeah.
So nothing was known before about learning a submodular function?
So there is a previous paper by Nick and Michel Gomez and a couple of others, but they're looking at exact learning with value queries. And so what they wanted is their model wanted to make sure that after they make a polynomial number of adaptive queries, they are within a certain factor of the target function everywhere, on every single subset of the ground set. And in their setting, it was much easier to get a lower bound, because just in learning, almost everything is difficult to learn in the exact learning model. Like even disjunctions are difficult to learn in the exact learning model, but trivial to learn, say, in the PAC model. And so, no, they're in the exact learning model. I actually think they got rid of, even probably, I'm not sure if it's probabilistic, the argument. It's not probabilistic. It's just approximately correct. I know, but.
You know.
Definitely approximately correct.
Yeah, right. So basically in that case, to prove a result in that case, you don't need to look at functions with just one bump. So I would call this a bump here. But to get a lower bound in the exact learning model, you just need to look at the function with one bump. And that's much easier. You need to construct a family of functions with just one bump, and that's much more easy to construct. So we initially, actually, to be honest, we initially had the upper bound, the square root of an upper bound, and we were hoping to reduce the upper bound to a constant factor. So we first worked hard to get a better upper bound, and then after a while we worked hard to get a better lower bound. And so it turns out that n to the 1/4 is a lower bound. All right, and I would like to quickly talk about some of the, to give a high-level idea about the type of matroid we use. And so just to remind you, what is a matroid? It's a combinatorial structure that generalizes the notion of independence in a matrix. And formally, it's a pair given by a set V, ground set V. And also, we also have a distinguished family of subsets of the ground set that satisfy two axioms. The first one is that the subsets of the ground set subsets of independent sets are independent, and the second one is that if I and j are independent, such as size of I is strictly smaller than size of j, then we can always augment I with an element from j minus I and still maintain independence. Right? And clearly an immediate consequence of this second axiom is that all maximal independent sets have the same size. Now, the rank given a matroid, you can define naturally the rank function of that matroid, which is defined as the rank of S is the cardinality of the largest independent set contained in S. And as I mentioned a few times, it's well known that this rank function is submodular. And the classic example of a matroid is a uniform matroid, where it's the simplest possible example probably. So here the ground set is given by elements 1, 2, 3, and so on n. And the independent sets are the subsets of the ground set of size at most k. Yes?
So if in your setting you were to take the D to be the uniform distribution, and you were to set epsilon to be like less than 2 to negative n, would you recover the results of the Goemans, the earlier paper?
No, because because if we go back to our picture, our construction, so if you ask, is our construction.
The algorithmic, like, would you then?
Well, no, because no. Algorithmically, no, you will not recover because remember the number of examples you need to see is like n over epsilon. So if you set epsilon to be 1 over 2 to the n,
so
then it's not polynomial anymore.
So in the log 1 over epsilon.
No, it's no log 1 over epsilon. It's n over epsilon.
Okay.
So it's n over epsilon times log 1 over delta. Delta goes into the log, but epsilon goes into, it's like 1 over epsilon. All right, now actually well-known generalization of uniform matroids in the well-known class of matroids is the class of partition matroids, where you have k disjoint subsets of the ground set, A1, A2, AK, and we also have k numbers, U1, U2, UK, such that for each I, UI is upper bounded by size of AI minus 1. And then the independent sets here are those subsets of the ground set with the property that the cardinality of the intersection between I and AJ is upper bounded by UJ for all J. And one can easily verify that in the case when these sets are disjoint, we get a matroid. If sets A1, A2, AK are disjoint, then we get a matroid. However, if the sets are not necessarily disjoint, then we might not get a matroid. And here is a simple example. So just imagine n is 5, A1, so the ground set is given by elements 1, 2, 3, 4, 5. A1 is the set 1 to 3, and A2 is the set 3, 4, 5. And let's set U1 and U2 to be both 2. Then it's simple to see, but both sets 1, 2, 4, 5 and 2, 3, 4, so these are both maximal sets in this family. However, they do not have the same cardinality. And this contradicts one of the matroid properties. Right? So if the sets are not disjoint, then we might not necessarily get a matroid. However, it turns out that for k equals 2, if we further impose a constraint on the cardinality of the intersection between I and the union of A1 and A2, then we get a matroid. So essentially, if we impose a constraint on the cardinality of the intersection between I and A1, and the constraint on the cardinality of the intersection between I and A2, then we also need to impose a constraint on the cardinality of the intersection between I and union of A1 and A2, and this constraint has to somehow depend on the intersection of A1 and A2. Right now, in our work, we generalize this from just two sets, A1 and A2, to the case where we have many sets, A1, A2, AK. Now we need to impose constraints on the cardinality of the intersection between I and union of many sets, AJ. Right? So, for instance, let me denote by a capital J is the union over set AI over I in index set J. And so you have to impose, for any subset J of the ground set, we have to impose such a constraint on the cardinality of the intersection between I and this set AJ. Now, what constraint we impose? Well, ideally, we'd want just this term over here, sum over J of Uj. But this doesn't work even for k equals 2. And what it turns out to work is to add this correcting term over here. So, and this term here is 0 when the set, it's always negative, so smaller, yeah, smaller than or equal to 0. And it's 0 when the sets are disjoint. And it's close to 0 when they are nearly disjoint. Right? And then we can show that this is a matroid. And technically for that.
So this specializes to the previous one when k equals 2, or it doesn't?
It does, I should.
Okay.
Yeah. Yeah? And, right. And actually, even this only leads us just partway through, because actually this construction requires that k is smaller than or equal to n. Because when k becomes greater than n, then this function f becomes negative, and so the family becomes empty. Okay, and so actually we had to do other tricks to actually allow k to be super polynomial. And I'm happy to talk about that offline, so the actual details are fairly complicated. So at the high level, what we had to do is to somehow truncate the function f in a way that ensures that we can get rid of some of the constraints.
N has the number of elements in your universe, and k is the number of partitions.
Yes, yes, yes. And again, this only allows us to deal with k smaller than n, but for our lower bound, we really need k to be super polynomial, and so we had to do further tricks to really go there. All right, but after further tricks, right? So we get to this picture. We manage to show that there exists this set A1, A2, AL. These are subsets of the ground set, right? And there are super polynomial many of them, and there exists these two values high and low, such that for any assignment of high and low on these sets, there is a matroid in our family whose rank function achieves that assignment. And as I mentioned, this then implies our learning lower bound for learning. Right? And actually, I also want to mention, especially that Rakesh is here, and probably some others are here. So actually, interestingly, the lower bound also holds for gross substitutes. So this is a subclass of submodular functions, and I think it's usually believed to be much simpler than submodular functions, right? But the lower bound still holds for gross substitutes, just because one can show that the matroid rank function is a gross substitute function. All right. How many more minutes do I have? 15, okay. Yeah. Good. So, right, so to summarize the results for learning submodular functions, we had an n to the 1/3 lower bound. I think this is a really surprising part, and we also have a square root of n upper bound. Right, and for the remaining time, I want to switch to talk about a different class of valuation functions, namely the class of XOS valuation functions. So it's all known that any submodular function is an XOS valuation, and any XOS valuation is a subadditive valuation. Now, a nice thing about these XOS valuations is that they come up with a natural representation. And in particular, a function is XOS if it can be written as max of sums, where the sums are allowed to overlap. Right? So for instance, assume that here f is a value of, say, a traveler on a bundle of vacation activities. So the items here would be the types of vacation activities, and each tree would correspond to a possible vacation site. And when the value, the valuation of the traveler on a set S will be the maximum value of the set S over all possible vacation sites. So for instance, here, in this specific example, the value of the function on the items 1 and 2 would be 16 because of the Switzerland tree, and the value of the function on the items 2 and 3 will be 10 because of the Romania tree. So here items 1 and 2, for instance, represent skiing and dining, and items 2 and 3 represent dining and sea cruise. Right, and so from a learnability point of view, what we show about XOS valuation functions is, so we have 3 results. So first, we can also show that there exists an algorithm for PMAC learning the class of XOS valuations with an approximation factor of square root of n. And in order to do so, we had to extend the structural result of Gomans et al. To XOS valuations. So the result again said that any XOS valuation can be approximated within a square root of n factor by square root of a linear function, and we extended that, and then using a similar trick as the one we had for learning subadditive and submodular functions, we get the square root of n upper bound here for XOS valuations. Now, so this is our general upper bound here. Now we can also show a nearly matching lower bound, and in particular we can show that any algorithm for PMAC learning the class of XOS valuations with an approximation factor, right? Any algorithm that only uses a polynomial number of examples can PMAC learn the class of XOS valuations with an approximation factor better than square root of n. And actually, the bound here, so it's better than the one that we had for submodular functions, and actually the proof itself is significantly simpler compared to the one that we had for submodular functions. And finally, actually, this is the most interesting result here. We can also show that if the target function has a small complexity, so in particular, for instance, if the target function is only given by a polynomial number of trees in its natural representation, then we can get a much better approximation. So we can get an n to the 1 over n to the epsilon approximation in time n to the 1 over epsilon, if this is for any epsilon. So and more specifically, actually, what we even show is that if the target function has at most r trees in its representation, right? So again, this is how next evaluation looks like. So if we have if the target function has at most r trees in its representation, then we get an r to the epsilon approximation in time n to the 1 over epsilon. And again, this is for any constant epsilon. So the smaller the approximation factor gets, the larger the running time gets. And just the high-level idea here, the proof idea here was the key insight was to show that the target function, which now is maximum of r additive functions, where r is a number of trees in its representation, has a property that its that its Lth power is approximated within a factor of R by a linear function over extended features, over all tuples. So right now we're going to have n to the L tuples, one for each subset of at most L items, and then the value of the feature on a given set will be 1 if all those items belong to the set and 0 otherwise. And so again, what we can show is that the Lth power of the target function can be approximated within a factor of R by a linear function over these L tuples. And so think about L here being, for instance, 1 over epsilon. And then using this result, together with the similar trick that we had for learning submodular and subadditive functions, we then get the desired learnability result. Right, and I guess from a conceptual point of view, this result highlights the importance of considering the complexity of the target function for learning. And actually, it will be interesting to discover somehow a natural representation for submodular functions where we have more complex and less complex submodular functions, and to maybe try to get a similar result also for submodular functions. So I mentioned earlier that any submodular function is an XOS function, but the representation is, uses an exponential number of trees, so that's not the right representation if you want to think about submodular functions. Right, and actually, as I said, so we can get a target. So we can get a target-dependent upper bound. So functions with smaller complexity are easier to learn, can be learned better. And in the worst case, however, we get a square root of a lower bound for these XOS valuations. And actually, this proof is really simple. So I'll just quickly go through it. It's a simple probabilistic argument. So the main idea here is just to use the fact that when n is large enough, there exist subsets A1, A2, AL, super polynomially many of them, such that two facts happen. The cardinality of each AI is about square root of n, and the cardinality of the pairwise intersection is upper bounded by log n for each pairwise intersection. And this can be easily shown just by constructing each set Aj by adding probabilistically each element of the ground set, say with probability 1 over square root of n to that set, when we get these properties. Now, given this family, we can now construct the hard family of XOS functions that has a property that, again, there exists these super polynomially many subsets of the ground set, and there exists these two value high and low, such that for any assignment of high and low in these sets, there exists an XOS function in our family that achieves exactly that assignment. And so in particular, for instance, let B be an arbitrary subfamily of these sets A1, A2, AL. And here's how we can construct an XOS function that achieves high value on sets that belong to B and low value everywhere else. So all we have to do is to just add an OR tree for each set AI that belongs to this set B. And in this OR tree, we're going to include all the elements in AI, right? Where again, AI belongs to the set B. And the value of all those elements will be set 1. And then just by the definition of an XOS function, we get that for all AIs belonging to this set B, we get that f of AI is the cardinality of AI, right? Because it's again a max of sum. This is the value of the function. And for any AI not in B, we get that f of AI is upper bounded by log n, and this follows from this upper bound on the pairwise intersection, right? And now given this, given this, I mean, this immediately gives us this picture over here that says that there exists this super polynomially many of sets, subsets of the ground set, and these two values, such that for any assignment of high and low of those values, we get an XOS function that achieves that assignment. And as I mentioned a few times already, this then immediately implies the lower bound for PMAC learning with a factor of roughly square root of n. All right, so and actually I just want to quickly also mention that the functions that use in this lower bound are not submodular. Right? That's why the lower bound does not apply. Also, this construction does not apply to submodular functions as well. And one can easily see that just by considering, say, a function that is specified in our family that is specified by two sets AI and AJ. Without loss of generality, we can assume that item 1 to 3 only belongs to AI, while item items 4, 5, 6 only belong to aj, and then just by the definition of an XOS function, we get that g of 1 say is 1, g of 1, 4 is 1, g of 1, 5 is 1, and g of 1, 4, 5 is 2. And so we get that the marginal value of 5 given 1, 4 is greater than the marginal value of 5 given 1, and so this is not submodular. All right, so to summarize, so in this work, we analyze the intrinsic learnability of interesting classes of valuation functions, and we provide nearly tight upper and lower bounds on their learnability. Now, our analysis has implications in various fields, in machine learning through the PMAC learning model, also in optimization, and in particular, our construction, our lower bound construction for submodular functions really reveals interesting, novel extremal properties of submodular functions. And this should be of interest across many fields. And actually, I know that Noam-Nissan and Tim Ravgarden already use this lower bound construction to show some lower bound for allocations in combinatorial auctions. And finally, also hopefully these results also have some implications in algorithmic game theory, right? And hopefully some of these techniques could lead to algorithms for improved economic decision making. And in terms of open questions, because maybe I'm sure that many of you here want to solve some of them. So actually the most interesting question is really technical question is to improve is to bridge the gap between our upper and lower bound for submodular functions. And in particular, it would be interesting to show that a lower bound of omega of square root of n for learning submodular functions. So
you believe the right answer?
I believe so, right? Just because for XOS valuations, we have square root of n was the right answer. But for sure, our construction doesn't go through. We optimize it as much as possible. So one would need a completely different construction based on a completely different family of matroid.
And why did you get 1/3?
Just comes from optimizing the parameters, so it's not. It's hard.
There's nothing.
No, yeah.
There's no insight into it.
No insight into it. Or no easy insight.
Okay.
Right, and it would also be interesting, so as a second question, it would also be interesting to analyze PMAC learnability of other interesting classes of real valued functions. All right? Questions?
So in the supermarket example, at the end, after learning all this submodular valuations and so on, if you still sort of have to go back and just give an individual price for every item, is this an overkill? I don't know, maybe you know, maybe Ricky knows. Say about this. So so are we learning anything useful by learning the entire submodular function, given the fact that finally the pricing has to be done on an individual item basis?
Well, you can, for example, target advertising better, right? If I know your valuation, I can, it's not necessary for pricing, but there can be other things I want to do once I know your valuation, right? I can target advertising, coupons.
We certainly care about that, like with online advertising. We have people working on that.
But actually, a valid question related to that is, so at this point, I assumed that I get to see the value of the function, the target function given a set S. But in real world, you don't really see the value of the function. You only set prices, and you get an approximation of the value of the function. So that's
so you get a lower quantity, something which is at most the value.
Right. If the user buys, if the user doesn't buy, you only know that the value of the function was higher. If he buys, you get some approximation. And actually, so that would be an interesting question. Can you learn if you only have can you learn only based on prices? And I have a partial answer for that.
Your learning algorithms seem to learn based on only the label saying, is your function high enough or is it low enough, right?
So if you know the set S, right? So if you know, so this is I was about to answer this. So if you know the set S that the user is contemplating buying, for instance, on Expedia or Orbit, I propose a deal and I can just observe if the user is interested in it or not. So if I know the set S, then the upper bounds would go through. So I just based on the kind of the intuition that you had. If you don't know the set S,
if you went and bought a certain set, implies that you didn't buy any superset. Probably gives you lots of negative examples, right?
Well, the specific model that right, but
why didn't I buy the other things? Because the values, my valuation was less than the price.
Right, but those negative examples are not necessarily IID, so.
They're not independent, right?
But it also could be a run out of money, right? So it's not just you don't want to.
Not if you're submodular. You're not allowed to run out of money.
So what's your problem for the subadditive class?
So actually the way I presented it, so it's n. However, actually one can show, even for subadditive I now know a complete answer. It's actually the right answer where is square root of n, about up to log factors. So actually Tim Rapgarden pointed to me that he has in a paper a structural result that says that any subadditive function can be approximated within a log n factor by an XOS function everywhere. And given this and the results for XOS functions, also we get a square root of n times log n upper bound for subadditive functions, and or lower bound is square root of n over log n, so up to log factors, square root of n is the right answer there.
But suppose your family, instead of the max of sum, is max of sum of some submodular function. Namely, you're not adding up the item. Your item can be broken up into subsets somehow.
Yes, so that's a great question.
So does that come closer to the sum of max of sum, or closer to just general subadditive?
Well, I'd have to think about it to answer it. I mean, I've never thought about best class, so I only looked at classes that are known in the literature, and that one is not known, but to be interesting, it's a great question.